quantum computer, atoms would be your qubits or your nodes, and you'd be coupling them with photons, which are your flying qubits, taking information from one node to another. And we build atomic clocks, which are important for metrology applications, and so on. So atom-photon interactions are important, but I gather you would have sensed a but coming. They're also very inefficient. This goes to the fundamental weakness of light-matter interactions. The fine structure constant is small. That's a fact of life. So we need to do something to be able to enhance these interactions. And one thing that we can do is to confine electromagnetic fields in smaller and smaller regions of volume. So in a way, you can think that atoms and photons can see each other better, right? So this brings us to nanoscale quantum systems, which allow for efficient and tunable light-matter interactions. Now, a lot of these applications that I mentioned also require us to connect quantum systems at long distances. And you may have heard in your electrodynamics courses that, you can think of atoms as dipoles semi-classically, dipole-dipole interactions in free space. Scale is 1 over distance cubed. So you can't go very far, and you need something like a telephone line, which is what waveguides provide us. So in order to be able to connect distant quantum systems, build your large-scale quantum networks, and so on, we need waveguide coupled atoms. All right, so these are the two regimes or kinds of systems that I'll talk about today. And particularly in the context of nanoscale quantum systems, I'll discuss the role of quantum fluctuations and how can we control them. And in the context of waveguide coupled atoms, I'll talk about when you go far, what is the role of memory of the electromagnetic field, okay? Which is, in other words, known as non-Markovian effects. We'll discuss that as we go. So in the first part, we'll be shrinking things down, and in the second part, we'll be stretching things out, and we'll specify what I mean by long distances, etc., as we go. Okay, so to start with, nanoscale quantum systems are great. They provide efficient, tunable light-matter interactions. Here are a few examples. And these are just some theorist cartoons, but these systems are very much real. They've been realized in various experiments, even by butterflies in some cases. You can see the nice photonic crystal structure in the wing of that morpho butterfly, which gives it the cool blue color. And they're also important for applications. So in building single photon devices and sensing gravitational fields and so on. And so another reason why we want to go towards nanoscale systems, other than achieving efficient light-matter interactions, is a more practical one. So if you walk into a typical quantum optics lab, it looks like a jungle of big, bulky optical elements. At least it looks like that to me as a theorist. So what we'd like to do is to shrink things down to the size of a chip. And as we do so, we run into atom surface interactions at nanoscales. And as one goes into these nanoscale regimes, quantum fluctuations become important. And for those of you who are not familiar with quantum fluctuations, in quantum mechanics, or in quantum electrodynamics rather, nothing is not nothing. So even if you have empty space, which is completely devoid of all matter, all radiation, there are quantum fluctuations that come out of nowhere and go back to nowhere, okay? And these fluctuations have physical effects, which are pretty ubiquitous over various scales. In fact, all the way from the atomic scale, where we observe spontaneous emission of atoms. You excite an atom and it radiates its energy, and Lamb shift, Lamb, who's our local Nobel laureate, to the size of the universe. So it is conjectured, for example, that what you're looking at here is the cosmic microwave background radiation, which portrays the temperature fluctuations in the early universe. So it's kind of like a baby picture of our universe from 300,000 years or so after the universe was after the Big Bang. And these fluctuations can be correlated with what was the distribution of matter, and which is what the inhomogeneity in the distribution of matter is what led to formation of galaxies and stars and eventually us. So in a way, we can think that we are all quantum fluctuations. And somewhere between atoms and the universe, there are geckos. And if you have wondered, for example, how does a gecko climb on walls? Geckos have teeny tiny hair on their feet, which have van der Waals adhesion strong enough to be able to support their weight against gravity. And in the field of biomimicry, there has been some research where people are trying to create gloves for humans with a similar structure so that potentially people can walk on walls. And here's a relevant quote from the biologist who's been working on these gecko adhesion. Sorry? Yeah. To give you a bit of historical context of these quantum fluctuation phenomena, and particularly quantum fluctuation forces, let's go back to 1948 to a glass of milk. Actually, it wasn't milk, but it was some other colloid. Milk is also a colloid. In Phillips Labs, in the experimental group of Theo Overbeek, they were studying why are certain colloidal suspensions stable, which is a pretty mundane question if you think about it. But the idea was, if you consider two colloidal particles that are observed to be at a certain distance, and if you assume that the interparticle potential scales as 1/r⁶, which we know is the quasi-static van der Waals potential between two particles, you get forces that are too strong. And if that is the scaling, then this colloidal suspension should just clump together. But back then, Casimir and Polder, these two theorists, they did a QED calculation, including finite speed of light, et cetera, to show that actually this scaling should be 1/r⁷, not 1/r⁶. And this is the first paper that Casimir and Polder wrote, which describes the fluctuation forces between two particles. And there's one lesson here, which is, if speed of light wasn't finite, we will not have milk, among other things. Yes.
Repulsive potential at smaller scales, and then it works out like a van der Waals.
The repulsive potential, if I recall correctly, that is from the charges. But yeah, the catch was that the scaling has to be 1/r⁷. Otherwise, if you take 1/r⁶, it's not able to overcome the repulsion, and you'll just have the colloidal particles clumping together. I really like the story because it's kind of, they dug into somewhat of a mundane question and came up with quantum fluctuation forces.
And these fluctuations are what causes the potential to scale as 1/r⁷?
Yeah. Okay, so you can, maybe we can discuss this later, but it's very quickly, it's a factor of c, speed of light, which doesn't come for free. So you have to get a 1/r dimensional analysis. Yeah. Okay, thanks. Right, so shortly after this, discovery, apparently Casimir was taking a walk with Niels Bohr. I'm told Niels Bohr liked to take walks. And he mumbled something about 0-point energy, and which inspired Casimir to write this famous Casimir effect paper. It's just 2 pages, by the way, and it's really nice. If you're interested in these kinds of ideas, I strongly encourage you to read this. What he did in this particular paper was to consider a cavity formed by 2 perfectly conducting plates and look at the 0-point energy of the electromagnetic field modes with and without these plates, okay? And if you look at the energy difference, which is what's shown there, you find that this energy difference depends on the separation between the plates. And if there's an energy difference that depends on a separation, there's a force. So this is the famous Casimir force, and in this paper, he also made some estimates and said that, although this is small, the experimental confirmation might not be infeasible. And for some, typical numbers of, let's say, a centimeter by centimeter plates separated by a micron, this force comes out to be 0.013 a number I don't have any feelings for. So if you want to know what it is, it's about 1,000th of the weight of a housefly, okay? Right, so Casimir force has, of course, been experimentally observed. And typically, the context in which we discuss these quantum fluctuation forces are with macroscopic bodies. So plates and plates, spheres and plates, spheres and spheres, etc. Separated by just nothing, which is vacuum electromagnetic field. And when we come to these nanoscale quantum systems, what we are thinking about is replacing one of these boundaries with a quantum system, which can be a collection of atoms, some solid state emitters, or a nanoparticle that is prepared in a macroscopic superposition, etc. Okay, and in such nanoscale quantum systems, these quantum fluctuations not only lead to forces, but because it's a quantum system, you also lose energy and quantum coherence as a result of the interactions with these quantum fluctuations, okay? And not, so these effects need to be mitigated in some way. And what is interesting now is that we can actually use the fact that it's a quantum system, and we can use its quantum properties to control these fluctuation-induced phenomena. And to give you some feeling for why do we need to control them, we can make a bit of a hand, back of the envelope estimate here. And if you take nothing from this talk, this is a good message to take. A back of the envelope calculation of fluctuation forces. So think of an atom in front of a surface as a dipole staring at a mirror. And you can see from image theory that this dipole in the near field regime interacts with a potential that should scale as 1/z³, right? This needs to have dimensions of energy, okay? And what might that energy be? The energy that characterizes the strength of interaction between this dipole and the vacuum field is given by h bar gamma naught, where gamma naught is the rate of spontaneous emission. Okay, so this gives us a characteristic energy scale. We also need a length scale. This is still not the right dimensions. And the only meter stick that this dipole has is the frequency at which it radiates, which is its resonance frequency. So we stick the corresponding, wave vector in the denominator. And actually, this isn't far from the exact Casimir-Polder potential of a 2-level atom near a perfect conductor. It's only a factor of 16 away. And I can also explain that if you talk to me later. So you can take this very simple expression and you plug some typical numbers, let's say for rubidium atom placed at 10 nanometers away from a surface, and you see that the potential that results from this vacuum fluctuation mediated interaction is about 10 millikelvin or so, which is large compared to the kinds of forces that we can exert with lasers and magnetic fields. Okay, so we need to do something about it, and you can see more clearly here. Oops, where is there a pointer? Ah, there it is. Okay, right. So you can see in this picture that what all these points show are various near surface atom traps and their characteristic strengths, which is overcome by this vacuum fluctuation forces at distances of 100 nanometers or so. So if you want to go closer than 100 nanometers, you have to do something to, you have to do something about these quantum fluctuation forces, okay? And that is why we would like to be able to engineer these forces and keep our quantum systems trapped at distances below 100 nanometers or so, keep them coherent, and so on. And how do we do that? We take an open quantum system perspective, which is to say that we think of our quantum system as the system of interest. It's interacting with the electromagnetic field, that's the environment, and the field modes are shaped by the presence of a certain boundary, okay? And in this picture, you can see that we can do various things. We can modify the properties of the boundary. We can change the optical material properties, etc. We can change the system bath interaction, say from electric to magnetic and so on. We can do more quantum things too, because we're talking about a quantum system. We can drive it with an external laser, or we can use entanglement in our system, which is a truly quantum feature that one can leverage, okay? Now, this is not an exhaustive list of the number of things you can do in this situation, but it kind of provides you a framework for trying to engineer and control nanoscale quantum systems using the toolbox of open quantum systems that's available to us. And so in this spirit, we've been looking into various systems and various problems, which I don't have the time to go through all of them, but if you're interested in any of these ideas, please come to me and I'm happy to have a chat. Today, though, what I want to focus on is I'd like to mention this idea of collective effects in Casimir forces and fluctuation forces, and a little bit about shaping interparticle potentials in nanosphere systems. All right, so collective effects in atomic systems, it's an idea that goes back to 1954, which is that if you have n atoms that are prepared in some sort of a correlated state, you can think of these as dipoles, basically. So if you have dipoles that are radiating, and they're radiating in phase, there will be a constructive interference in the resulting light that comes out of the system, which can be larger. And this is something this is an effect known as super radiance. On the other hand, if you have two dipoles that are radiating out of phase, there's a destructive interference, and you can in fact have a situation where no light comes out of an atomic system, okay? So such collective effects in spontaneous emission have been known for some time, since 1954. Breaking news, in other words. And if we take such collective atomic states and we put them near a surface, one can expect that because there's an analogy between fluctuation-induced forces and fluctuation-induced dissipation or spontaneous emission, there will also be collective effects in these vacuum forces, okay? And indeed, that's what we find. So this is, by the way, a manifestation of quantum correlations between these particles, and we'll see what the essence of this is in via this toy model. So let's take a toy model. You have a red atom and a blue atom interacting with quantum fluctuations of the electromagnetic field. You put this two-atom system near a surface, and you prepare these atoms in correlated quantum states, where you have a superposition of blue atom being excited, red being ground, or blue being ground and red being excited, with a positive or a negative sign, okay? Now, what happens in such a scenario is that you can have scattering processes where these atoms will exchange an excitation with each other, which will bounce off the surface. And these processes can interfere either constructively or destructively, depending on what's the symmetry of this state, okay? And this constructive or destructive interference of processes at this state level, as you can see, leads to constructive or destructive interference in the forces experienced by these atoms or the collective spontaneous emission of these atoms, okay? So what I'm plotting here is when the two atoms, the red and the blue atoms, are prepared in a super radiant state where they're positively correlated, there's an enhanced force, attractive force, as well as an enhanced gamma, which does nobody no good. On the other hand, if you were in a subradiant state, you can see that you kill the forces. Well, if you are infinitely close, which is not practically possible, then it goes all the way to zero. And at the same time, you have zero spontaneous emission. So your states are long-lived as well, which leads us to investigate these subradiant states further. Yes.
I'm just thinking of it classically.
Yeah.
If they were aligned horizontally, not vertically, like in this picture, then you actually have the opposite already.
Yes. Okay. This is a very good question, and it goes to this idea of, is your atom going to behave as according to its correlation with its image, or according to its correlation with its entangled counterpart, right? Which is it more narcissist or more monogamous or whatever, right? So this is yeah. So the answer to that is that it depends. We have done these calculations. It's a really interesting question, but the details vary depending on the specific states and parameters.
I can compare a state where, there's no, you haven't talked about phase locking, right? So like that, yeah. Right? So then maybe experimentally I can force the dipoles to, with a high enough electric field, to orient in a specific direction.
I see.
But then I'll have to use it like a laser that's behind this or something like that. And now it's proper not superfluorescence. In other words, there's no phase locking that comes over time. Now in that case, it's hard for me to prepare them out of phase if they're very close to each other.
Correct.
Experimentally.
Yes.
But if they're parallel to the surface,
right,
then it's potentially easier. That's one thing.
Okay.
The other thing is, vertical dipoles are hard to even exist in nature on their own. 2D materials usually have in-plane dipoles naturally. Like whenever you excite an exciton, they would have in-plane dipole.
Okay.
So it might be just more interesting.
Yeah,
as a case to look into.
That's interesting. We should talk more about it. I'm very curious about that. Cool. Thanks. Right. So digging more into the subradiant state, by the way, what we can see is that for somewhat realistic numbers, if you're in a solid state, let's say 2 emitters inside a diamond, nano diamond separated by a couple of nanometers, which is 10 nanometers or so away from a surface, you can suppress both the forces as well as the spontaneous emission by a factor of 100 or so, which can be useful for making nanoscale traps. Now, switching gears a bit to a somewhat larger system, can't quite see, there's a tweezer field that's trapping the nanosphere there. So I also want to discuss a bit the systems of levitated dielectric nanospheres, which are fairly macroscopic objects. So this is, a silica bead of about 100 nanometers or so. You can use your standard laser cooling and trapping toolbox to bring these particles down to their center of mass ground state, which is pretty cool, right? So it's a fairly macroscopic system that you can bring down to its center of mass ground state. And what it allows us is that it opens a somewhat interesting regime of physics, which is this regime of gravitational quantum mechanics, meaning how massive a system can you take and how quantum can you make it, okay? So this cube, by the way, which I really like, this is a picture of, various regimes of physics, and the one that we are exploring with these massive systems brought to the quantum regime is the corner at the intersection of quantum mechanics and gravity, okay? And in this spirit, what you want to do is you want to take systems that are massive. So when, for example, you're thinking of atom interferometry experiments, these are 100 atomic mass unit systems prepared in meter-sized superpositions. People have also done interferometry with really large molecular clusters. And these nanosphere systems, they push the mass to 10 to the 9 or so atomic mass units, which is several orders of magnitude higher. Although, of course, the size of superpositions and coherence lengths that are achieved are smaller by also several orders of magnitude. And in such experiments, because they've done so much work to engineer all the sources of decoherence, there is an ever-present source of decoherence, which is quantum fluctuations that you cannot get rid of. So the questions that we ask in this context is, how do quantum fluctuations limit the size of these macroscopic superpositions? And in fact, you can even use these quantum fluctuations to engineer interparticle potential. So for example, there was a recent experiment also from the same group in Vienna of Markus Espelmeier, where they were able to tune interactions between two nanospheres. The eventual goal is to bring these particles both to the quantum regime and entangle them. And what we've been looking into in collaboration with the Vienna group is to create two particle bound states, which can be pretty deep, about 200 Kelvin or so. So this is just using tuning the laser properties and so on. This plot where by Clemens, whom you may have seen around OSC, is it shows that we can use these particle-particle phase correlations to suppress the decoherence of these nanospheres in a sort of collective manner. Right. Now, going back to these, atomic systems, while we were doing our collective effects near surfaces work, there was this experiment in Maryland where my colleagues, they demonstrated collective effects, collective superradiance and subradiance in atoms coupled to an optical nanofiber. That's the picture you're seeing here. And this was pretty exciting for me because, we were looking at collective effects near surfaces and we thought maybe there's something to be measured here. And one of the results in this paper was that they took the atomic cloud and separated it into two subclouds, which seemed to not affect the superradiance behavior. And because of that observation, they titled the paper as Superradiance Reveals Infinite-Ranged Interactions. Okay. Now, when we started discussing, we started questioning that title and got into a whole rabbit hole, which is, what if you take these atoms really, really far apart? And things do change. Okay. And this is the rabbit hole I want to jump into next. Yes.
Waveguide. I recall that superradiance, you can have superradiance if you're not satisfied in a particular condition where they're very close,
right.
As long as constructive interference can happen somehow, that they will interact with the same field mode.
Correct.
So then, in principle, they can be far without a common mode through a waveguide and still.
But there's the 1/r cubed still, right, in free space.
Yes, so what I'm saying is that it's not the dipole-dipole interaction type of deal, that you will still get superradiance if they're constructively interfering. And we think of it just a classical dipole, and it's separated with a distance such that there is a k vector where they would constructively interfere, then still you would enhance the overall radiation of that set of antennas.
You would enhance, but not perfectly. Right.
Potentially. I don't know.
There will be
you can do this when you get your lecture.
Sorry.
We can certainly discuss afterwards. Yes, so this brings me to the next rabbit hole I want to jump into of waveguide coupled atoms at long distances, and the idea is that when we are coupling two atoms over a very long distance, and by very long distance, the separation that I mean is this length scale v over gamma, where v is the speed of light in this waveguide, and gamma is the rate of spontaneous emission associated with the atomic system, okay? And as you enter these distances, what I'm going to argue is the memory effects of the electromagnetic field start to become important. You need to remember what did your field do in the as it mediates interaction from one atom to the other, okay? Just a brief introduction to what is this non-Markovian dynamics, etc., etc. So think of a quantum system, that ducky interacting with a bath, and the idea of this Markov approximation that we make very commonly in quantum optics is that any correlations in the bath decay much faster than system evolution, okay? So that you don't have to remember what happened in the environment. It's a pretty forgettable system-bath interaction, in other words. And your system can evolve based on whatever its state is now, and you don't have to, have any memory of its previous dynamics. Now let's think of the system that we are talking about. So we have two subsystems that are separated by some distance d that are interacting with this bath. And there's a time scale associated with bath excitations going from system 1 to system 2, which is this distance d divided by v. And there's a time scale associated with the system relaxation, which is just the inverse of its decay rate, okay? If we create a number, this dimensionless quantity that is the ratio of these two time scales, you can immediately see that if this dimensionless number is much, much less than 1, we should be Markovian. And it's actually also indicative of various ways you can go beyond Markovian, or you can go non-Markovian. So you can have slow bath modes, which is, it makes sense that if your photons are kind of lingering around your atoms, they should have the memory of what happened before. You can have strong coupling, where you have coherent exchange between system and the bath. That too is sort of memoryful. Or you can have retardation, which is the aspect that we are interested in, where parts of the system are far enough removed that you need to remember what happened before. Okay. Collective interactions between atoms have been explored in the context of structured reservoirs, where you have these slow field modes, also in the strong coupling regime. And what we are exploring here is collective interactions in the presence of delay or retardation. And why is this interesting? There's, of course, collections of quantum emitters coupled to waveguides. It's relevant for building quantum networks. I don't think I have to tell it to the CQN people here. And it's also relevant for distributed sensing and metrology-like applications. And it's not just relevant, but it can also be useful. So there has been some research before we jumped into this problem that also showed that delayed feedback can lead to generation of entangled photonic states, and also atom-atom entangled states. Okay. Now, to understand this problem, let's actually start with a toy model. So we have this, again, very simple system of just two atoms interacting via waveguide. And we prepare these atoms in a collective state, just like before. It's this excited ground plus or minus ground excited. Each of these is a two-level atom. Part of the field goes into the waveguide, and let's assume a part of the field can go out as well. And they're separated by some distance, which is long, as we defined long before. Now I'm going to show you some math, but I promise that this is, not math just for the sake of math. It will, I hope, lead to some understanding of the physics behind this problem. So you can describe this atom field interaction within a single excitation manifold, meaning that there's either one atom excited or the other atom excited with some probability amplitude C1 or C2, or there's one photon in one of the modes of this waveguide, okay, with some probability amplitude C omega. We can solve this. This is, just described by regular Schrodinger equation. So while the name non-Markovian open quantum system dynamics may sound fancy, it's actually not. So if you look at the couple dynamics of the two emitters after eliminating your electromagnetic field, you land with a very simple set of coupled delay differential equations here, which is why I think this is, a little bit of math here is helpful. You can see each of these atoms, according to the first term, just does its own spontaneous emission, and it has a little bit of a influence from the other atom with some delay, as you would expect, right? Now, this influence, of course, comes with some factors which depend on, what was the phase of the field and how it propagated from one atom to the other, and its coupling efficiency to the waveguide, etc. And we can solve these very simple coupled delay differential equations. These kinds of equations appear in a wide range of systems. Here's a list from Wikipedia, from instrument design to ADS-CFT correspondence, also in prey-predator dynamics. So we may as well be talking about, rabbits and foxes. Now quantization of rabbit is a different stuff, but the point is that the math is very doable and familiar. Okay, and if we look at the resulting dynamics from this delay differential equation, we find this exact solution where which we can understand pretty physically, actually. So what you're seeing here is that each of the atom updates its dynamics every time it sees a photon after a round trip time, or not a round trip, but like after the time it takes for light to go from one atom to the other. So what you're really seeing, what this collective dynamics is, it's a cascade of mutually stimulated emission between these two atoms. Or if you had more atoms, then that. Okay. All right. So with that, we can look at this more pictorially, and what I'm plotting here is the probability of atomic excitation for a super radiant pair of atoms. And you can see that if the atoms are infinitely far apart, which is this black dotted line, they do their own thing. They just emit exponentially at a rate gamma. Or if they're on top of each other, they emit with a super radiant rate, which is 2 gamma. So still exponential decay, but twice as fast. Now, if you look at one of the other curves, which is maybe, let's say, for eta equals 0.5 or so, the yellow dashed line, what it shows you is that they emit independently until they see each other, and then they exhibit a collective emission behavior, which is faster than regular superradiance. And this is something we call super duper radiance. And the reason for that is, hyper radiance and ultra radiance were taken by other people, so that's kind of what we're stuck with. Now, we can also understand this kind of dynamics from the perspective of the field. So what I'm plotting here is the intensity emitted by these atoms as a function of space and time on the x and the y-axis here. So what you're looking at is the two light cones coming out of the atoms. And as, again, these atoms see each other, there's a faster radiation outwards. On the other hand, if you look at a subradiant state initially, once the atoms see each other, they form a bit of a bound state. So you can think of this as a cavity that is being formed by the atoms, for the atoms, etc. Okay? And this inspired us into another rabbit hole, which I'll talk about briefly now. So this idea, it seems like it's a cavity, right? And what does a cavity have? Mirrors at each end. So here, these correlated subradiant atoms are behaving as mirrors. The idea that atoms can behave as mirrors has been around, it's not new. And there have even been experiments with, in particular, if you're putting a line of atoms at distances that are in a Bragg configuration. So just like you have a regular dielectric Bragg grating that reflects light, you can make a Bragg grating out of single atoms as well. And this has been experimentally demonstrated in waveguide coupled atoms that such Bragg atomic mirrors can reflect about 2,000 atoms can reflect 75% of the light back. Okay, and finally, this animation works. Seemed like it was stuck for a second. Right. Okay. So what we thought? Well, these atoms are also quantum systems. They are, not just regular classical dipoles. And what we can do is we can prepare them in quantum superpositions potentially. So if we think of a situation where such atomic array of, is made of, with each atom having distinct levels, one which is, let's say, coupled to the field, the blue one, and the red that is decoupled from the field. Okay? If I prepare all these atoms in the blue state, the light reflects, and if I prepare them in the red state, it transmits. So if it is a quantum system, I'm perfectly well allowed to put this in a quantum superposition of the two states. And what we get as a result is something that we call a quantum mirror, meaning that an object that can be in a superposition of being reflecting and transmitting at the same time. So we studied this problem of spontaneous emission in the presence of a quantum mirror. And indeed, if you prepare all your atoms in a superposition of being in the blue ground state or the red ground state, what results from this kind of dynamics is that a test atom, the green atom, for example, which is spontaneously emitting in front of this mirror in a superposition, by the way, will decay in a superposition of exponential decay or no decay. You can, this is somewhat of a new scenario. So, and you can also see this in the field that is emitted. In one case, the field just kind of forms a cavity, and in the other case, it's all over the place as it's, radiating light exponentially. Okay. Now, one very canonical example that comes up over and over again in quantum optics is cavity, QED, where you put atoms inside optical cavities. And here, what we've created is a cavity with two mirrors that are in superposition of being on, meaning being reflecting, or being transmitting at the same time. So as a result, you can have a quantum superposition of scenarios where your atom is actually decaying in a very good cavity, and therefore you should see a coherent exchange of excitation between the atom and whatever the cavity mode is. So, which is this phenomena of Rabi cycle that some of you may be familiar with. So indeed, if you're in the blue state, you see the Rabi cycle, the Rabi oscillations happen. And if you're in the red part of the state, there's an exponential decay. Okay. So this is sort of a new territory that we are exploring. It may seem a little sci-fi and a little crazy, but the ideas are not that far from what has been happening in experiments lately. So just last year, actually, there was this experiment in Munich where people demonstrated a coherently switchable array of Rydberg atoms that can behave as a mirror. And similar systems, or rather similar ideas, have been illustrated in a superconducting circuit system as well.
Rydberg
Yes.
atom to a waveguide?
Oh, this?
Yeah.
That's circuit QED.
Oh, circuit QED.
Yes, transmons.
Gotcha.
The idea there was you can kind of go between cavity and not cavity, and they saw coherent oscillations between those two. There is an atom, actually. The orange thing in between is another, it's a qubit. Yeah, yeah. Yeah, so these ideas, while may seem a little far-fetched, they're not all that far-fetched with the current experimental capabilities that we have. Now, going back to this, idea of retardation, we've discussed some interesting dynamics, but what is it good for? One can ask, well, you can generate entanglement with, it so happens, with extra delay. So one problem that we studied was, let's say you put two atoms in excited state, you let your system evolve, and you spontaneously land in an entangled steady state. And this entanglement, you can see, goes up actually with delay. So the more non-Markovianity and the more retardation you have, there's an optimal point, of course. If you're infinitely far apart, no light, no excitation remains by the time photon from one atom reaches the other. But after some amount of delay, you do build up more entanglement. And that regime happens to be non-Markovian. Now, coming back a full circle to the question that we started with, are dipole-dipole interactions infinite range? And the answer to that we found is no. There is a rangedness that comes from these non-Markovian effects, and we can actually write an effective dipole-dipole interaction Hamiltonian. And what you're seeing here, again, my cursor went away somewhere. I'm not sure where it is, but okay, there it is. Okay, right. So you can see in this factor of what I'm writing here is the effective dipole-dipole interaction. It goes down as you increase the delay between the atoms. And if this eta parameter is small, you don't see the effect of that delay, but in large non-Markovian regimes, it becomes relevant. Now, since how much time do I have? Almost none. Okay, I'm gonna wrap up soon. All right, so just to wrap up, we've seen these effects in experiments. This is fresh off the lab. The plot that you're seeing there indicates, photon correlation measurements with non-Markovian effects. And to summarize, we've, observed collective modification to collective atom-atom interactions in the presence of delay. We can generate entanglement using this delay. We've studied limitations to dipole-dipole interactions, and also this new territory of quantum mirrors that we are currently actively exploring. There are many questions that you may have, which I also have. How does this scale with number of atoms? Is there any use of this memory for sensing? And experiments, of course. We are actively exploring all these questions. This is actually a fresh plot from just this week where we've seen a signature of enhanced quantum sensing due to non-Markovian delays. Jenny, who's here, my student, she's working on creating atomic entangled states in these quantum mirror-like setups. And this is the next generation of the nanofiber experiment where we are trying to create switchable atomic Bragg mirrors. And Anyon is working on a non-Markovian spontaneous emission in atomic mirror-like systems. So with all that, I'll thank you guys and thank my group and my collaborators.
Very interesting, excellent talk. Q&A, so who is going to go first?
Talk, indeed. So returning to the picture that you showed about the the entangled pair of atoms in a mirror. So you showed that there is some sort of an indirect interaction channel between the two entangled atoms through a photon interaction with the mirror. But there could be also other channels of interaction. So, for example, the direct photon exchange between the two atoms or a non-radiative transition. So I'm just wondering how would these, if you take those into consideration, how would these affect the superradiance behavior?
If you are referring to the waveguide coupled?
No.
The nanoscale.
The nanoscale, yeah.
Okay.
So when you had two entangled atoms,
right?
Yeah, with a mirror. Yes, here. Yeah. So there was an image where you showed that there was a indirect. Yes, this one. So a photon transition from the first atom, right? So and then it gets reflected back to the second atom. So this is some sort of an indirect interaction, but there could be also direct
free space.
Yes, free space
exactly.
propagation. Yeah.
Yes. So I'm not showing that here because that does not affect your Casimir-Polder force.
I see.
But of course it exists. So there's the free space regular dipole-dipole interaction, which goes in these bare gammas. Or rather, actually, each of these has a surface-mediated and a free space part. Yeah.
So other channels also to be the thread, the non-radiative transition between the two atoms. So these are can be also modeled within.
We should be able to model them, but here what I've only considered is just the radiative part. Yeah.
Great talk, completely new concept to me. Just curious. So when we talk about these third states you're talking about for colloidal substances, is that meant to be interpreted as occurring at the boundary of the two solutions, or?
Let's go back to that. So the idea there was, my computer's being a little slow. It will show up. Okay, yes. The idea there is that you have two particles that are, let's say, at a certain characteristic distance, and what are the quantum fluctuation mediated forces between them. So what quantum fluctuations would do is that they'll spontaneously polarize an atom, go from here to there, and then come back. And if you don't account for these finite speed of light effects, your scaling is different. And that is what leads to a 1/r⁷ potential versus a 1/6 potential. Yeah.
So then if you change the polarity of anywhere along the path or the original particles themselves, would that affect forces we're describing.
You mean how these dipoles are polarized if they have a permanent dipole? Yes. Yes.
And that's what you guys are kind of what you're experimenting into controlling the media.
You can use, so for example, as Mohammed was pointing out, if you change the dipole orientation, one thing you can see perhaps immediately is that if there's a dipole like this in front of a planar surface, its image dipole is like that.
Yeah.
And they add up to 0.
Yeah.
So you can kill spontaneous emission of a dipole that way.
Yes.
Yeah.
You have to kind of pick unique geometries.
Yeah, so you can certainly pick your dipole orientation as one of the parameters that you can tweak among other things.
Thank you.
Yeah, sure.
Next question.
So yeah, I've asked a lot of questions so far.
Go ahead.
But yeah, for the super duper radiance, I would have probably guessed that this is going to happen from energy conservation.
You could have told me. I spent a month thinking my calculations were wrong.
So the reason why I'm saying this is because, for instance, the lifetime in super radiance, why it's shorter, it's from energy conservation, right? Because you have a stronger dipole, so you're going to emit in a burst, which means that you have to decay rapidly.
Yeah.
So the lifetime has to be n times the number of dipoles times gamma naught, the radial decay rate. So in your case, you're staying like a longer time, and then you're suddenly changing it. So then you have to decay very fast then, and then it will be faster than.
In hindsight, it seems intuitive, but at the time it was not. And I spent a month thinking my calculations were wrong. So
because you're doing calculations.
Yeah, but at some point I understood that it's plausible because you have another atom and it's kind of like a per cell enhancement. You can think of it that way. Right?
Yeah.
So then I realized that yes, this is plausible. But now we have more intuition.
So for this cavity bound state idea,
right?
Can one think of it as that there's destructive interference between the outgoing waves?
Yes, absolutely, it is.
In both sides.
Yes, yes, and that's precisely due to the correlations, the anti-correlations between the two dipoles. So the field that is coming, it's perfectly destructively interfering that way. And that is the same concept in these Bragg mirrors too, that you get all these partial reflections adding up back and canceling forward.
Yeah.
Yeah.
I have a quick question myself. So things become smaller and smaller, and then we always assume Markovian system. Now we have to assume non-Markovian system. That's the system becomes smaller and smaller, and bath becomes smaller and smaller. And we heard wonderful things about super radiance and sub-radiance. And what is the future of non-Markovian bath?
Future of non-Markovian bath. I think, okay, so to me, saying something is non-Markovian is kind of like going to a zoo and saying something is non-elephant. Because it's a lot of things are non-Markovian. So I think there's a lot of things that we can explore as far as from in the context of these retardation induced non-Markovian dynamics flows. I think there's a lot of things to understand, and in the context of still collective interactions or many body interactions. One thing that I didn't touch on is there are a lot of many body physics aspects also related to these collective systems. I've been talking about just 2 atom systems, but in that regime, one can go into the physics of phase transitions and so on. So I would think that would be an interesting direction to go towards.
Yeah, that's it. All right, so we have to wrap up, and it was really excellent.
I think Tom had a question.
Well, I was going to ask it. I think I recall you discussing at another time the mirrors. The examples you gave here were Bragg and a linear fiber, but are there some cases where the mirrors are actually 2-dimensional sheets?
Yes, absolutely. So I did have one picture of that.
It was the one on the paper you showed?
Yes. So I skipped that discussion for now because this would have been a right. So these are sheets, 2-dimensional sheets of atoms arranged at sub-wavelength distances that can effectively behave as a mirror. So one way to think about this is that this is a super atom, meaning that if one atom reflects light with some efficiency, if all these atoms are behaving cooperatively, that efficiency goes up by a factor of n squared. And yeah.
So what kind of, you were talking about 75% efficiency with the linear array?
Oh, yes. This has about, if I recall correctly, this kind of a system, there was a paper in 2021 that had the record efficiency of about 50%. So not great, but okay. Actually, in these pictures, maybe, no, it's very hard to read.
Yeah, so it's around what you said. The earlier paper I remember was around
Okay.
what you said, but theoretically it could reach to 90-something percent.
Yeah.
But the
Oh,
problem
yeah.
is atoms
Theoretically,
are
yeah.
jiggling around.
Yeah.
So yeah, I was gonna, so there's the 50% of that's just laboratory imperfections, or is it?
Yeah.
Okay.
How much is it based on the fact that it's a 2D structure? If you pull it out into 3D.
In 3D, then you'll have to also people have made Bragg mirrors with optical lattices where each sheet is a pancake. So that is a 3D structure. And if I recall what the efficiency was, a paper back in the day. I don't wanna.
Yeah, it's okay.
I would again say it's close to 70-80%, but don't quote me on that, please. Yes.
Someone write
Can we edit this out of?
Someone write that down. Fortunately, Kanu will be available forever to us. If you have any question, anytime, Kanu. Let's keep on.